So for every problem in this chapter, in the middle of the problem or the whole problem itself would involve something called a mole-to-mole conversion. So I try to simplify it as much as possible. I wrote it as 3A plus 2B make 4C. I just made up some numbers. But here's the thing I wanted to point out to you. When you're doing these problems, you know how when you write the chemical formulas, man, they just take a long time to write. So for example, if you had 3 hydrogens plus 2 nitrogens, and this one's actually fairly simple, make 2 NH3s. Like, to write all the formulas all the time takes a lot of time. And what I often tell my students to do, and my fellow teachers would probably kill me for saying this, I just call that A, I call that B, I call that C, and then I don't have to write them anymore, okay? So anyways, that's just a helpful tip, and I'll try to use it during this lecture so that you can see how useful it is and also how it cleans up all your calculations. It encourages you to write it out, okay? Anyways, so here's what we're going to do. This is my balanced chemical equation. And then I have to calculate the moles of B that are required to completely react with 3.75 moles of A. And then the next question says calculate the moles of B that are required, right, to yield 7.5 moles of C. So this is the beginning of every one of these problems, okay, these two problems. So this is how we're going to proceed with this. It's a mole-to-mole conversion. I have a balanced equation, so this is one of the things you have to have, like number one thing you have to have. The second thing you're going to do is you're going to start with moles of whatever you're looking for. But remember, always on the left-hand side, I always write what I'm looking for. And then on the right-hand side, I start with what I'm given. And then a mole-to-mole conversion is one step, okay? And you use the stoichiometric coefficients, right, and their mole ratios, the reaction ratios, to allow you to cancel out units and end up with units that you want. So I want to get rid of A, right? So I have 3 moles of A for every, right, 2 moles of B. So what I'm looking for over here, it has to end up at the top over here, right? So then the moles of A will cancel out. And then I can do my calculation. I'll just pull up a calculator real quick. So 3.75 times 2 divided by 3 gives me 2.5. Let me do it in blue. And if I'm following sig figs, it's 2.50, because there's 3 sig figs here, moles of B, the unit I'm left over with. Okay? So this is what I want you to do. I want you to start with moles of B. All right, and you have 7.5 moles of C. Set up your reaction ratio and calculate the moles of B it takes to yield 7.5 moles of C. So there's the problem worked out. And if you're looking at it, right, it's 7.5 moles of C. It's 2 moles of B for 4 moles of C. And I get that from these two values. And then I just do the math. And the math comes out to 3.75 moles of B. There's only 2 significant figures, so I round it to the 2 sig figs, and that gives me 3.8 moles of B. So this is what I want you to do. And so this problem is the bicycle factory, but with sort of a chemical reaction slant to it. You have 5 moles of A, right? And you have 4 moles of B. I want you to figure out what the theoretical yield, how many moles of C could you produce, okay? So this is the thing that I'll tell you, right? And then I'll let you try it. In the bicycle factory, let's go back up to here. I gave you both the reactants, right? And in your head, what you did was you calculated how much product you could make from each reactant. Now, in these first problems here, right, you weren't given 2, you're just given the 1, so you just calculate from the 1. But now that you're given 2, what you have to do is you have to calculate the moles of C that you can get from A, and then the moles of C that you can get from B. And then when you get those two numbers, you need to figure out which one is the theoretical yield, which is the most you can make in this reaction, okay? And then I'm going to stop it here. I'm going to let you try that. And then when I start it, I'll have worked out the answer and we'll talk our way through it. It's very important that you don't just like run through this particular one and just sort of assume that, oh yeah, I'll remember that. I actually will recommend for a lot of these kinds of problems, it's very hands-on. You have to do it and then you'll remember it, okay? All right, so here we go. So you're going to calculate moles of C from 5 moles of A and moles of C from 4 moles of B. I pulled the reaction ratios or the mole ratios from the balanced reaction. There are 4 moles of C for 3 moles of A, for example. And I get 6.6. That rounds to 7, but I decided not to round it at this point. And then 8 moles of C, right? So which do you decide? It's this one, right? Because when you make that much C, because you got to remember, every time you're making some product, some reactant gets used up. And eventually, I get to 6.6 moles of C. All of the A that I had is used up, and so the reaction has to stop. Common mistakes for people are to choose the one that's bigger, because they think theoretical yield is the most you can make, so they just take the bigger number. And the other mistake that people make is they add the two numbers together, and for most people, that doesn't make any sense. Even for the people who do that when they do it, afterwards they go, that made no sense. I'm like, well, at least you realize that. But it's always the smaller of the two numbers. Your limiting reactant then would be A.